Hello. Good evening, morning, afternoon. Today we're going to be covering assignment number 3. Now, this is an assignment that was due September 18th, but as of recording this, it's only been a week, so I figure an overview video could be useful to some of you guys. Now, as of this point, your evidence notebook should have 4 assignments in them, 6 sets of notes, and if you have all that, good job, you're caught up. Your table of contents should look something similar to mine. If you got a little bit of extra stuff after the vocab or after anywhere, just go ahead and X that out. We're going to put this off to the side here. Zoom in a little bit. There we go. So, as per usual, your typical first kind of question is always going to be vocab. So this is vocab number 7 through 9. So what is that going to look like? I should just use my handy dandy table of contents to get there. So 7 through 9, we've got potential energy, kinetic energy, and conversion factors. The focus of this assignment really is going to be on the conversion factor. It's useful to have knowledge of potential energy and kinetic energy, but it's more useful, in my opinion, to be able to do something with that, and that is going to be done through these conversion factors. We're going to be putting things such as chemical energy, which is a type of potential energy, and we're going to be using it for, a purpose, something we can use, and that's typically mechanical energy, which is a type of kinetic energy. And so we are able to convert those things through these conversion factors. So we're not going to assignment 4, we're going to assignment number 3. That. Okay, vocab. Needed a definition and an example. Head to page 16 and 20 in your book to get the definition, and you make your own example. So for numbers 2 through 4, we'll be using these formulas, 1, 2, and 3. They're all basically the same formula. It's the formula for density. And so as 1 reads, to find density, we need the mass over the volume. To find mass, we need density times the volume, which is just this equation rearranged. Basically multiply both sides by volume. The volumes here cancel each other out, and so we're left with density times mass, or density times volume equals mass. For the other one, if we want to rearrange it again, we want to figure out volume, we divide both sides by density, and so volume is left alone, and mass over density will equal our volume. All right. So to do this in class, I had you guys do polls, and for the most part, you are on the right track. A sample has a volume of 60.5 milliliters and a density of 1.2 grams per milliliter. What is the mass of the sample? Well, if we need mass, we're just going to use our second equation here. So I'm going to highlight this, have our answer be highlighted. Our mass is going to be equal to density times volume. We have 60.5 milliliters, that's our volume. Our density is 1.20 grams per milliliter. That's going to equal, and let's just have the calculator pulled up actually. Let's just pull up a calculator app. Great. Off to the side here. And I believe number lock works. So 60.5 times 1.2, 72.6. 72.6 grams. Another way to do this, and I'm going to do 3 different methods for this. Another way to do this would be to insert a equation. And so we have 60.5 milliliters. We're going to be multiplying. So go up to where you see my mouse, multiply by 1.20. And here's where this becomes handy. We're doing a fraction here. Let's do it this way. We're doing a fraction, 1.20 grams over milliliters. And so this way, we have our milliliters cancel each other out, right? And when they do, we'll still get the same answer. 72.6, but in this case, we're very sure it is grams. And the last way I'm going to do it is the table method that some of you might know. We're going to need 3 tables here, and it's 3 by 2. 60.5 milliliters go on top, 1.2 grams. And if you ever see grams per milliliter or grams or miles per hour, then that just means you have 1 milliliter on the bottom. And so our units here will cancel each other out. Milliliters cancel each other out because you have one on top, one on bottom. And so our final units are in gram. We're going to get 72.6 grams. So we have 3 different ways to show the same thing here. These 3 are starting materials. I'm just going to cover that in green. There's no math being done. We're just going to color this one in red. That's where we end. So we've got 3 different ways to show the same thing. An equation, in just inline kind of text type deal, and a table. We're not going to do as much for the next 3, or next 2. We're just going to do it inline. So we're going to space out, highlight the answer. We have a 4.8 gram piece of magnesium, and it's displacing 2.76 milliliters of water. So that word, displace, let's draw it out. I've got a beaker. Inside that, okay, hold on here. Inside that beaker is a set of water. And let's fill the thing. All colors. There you go. Inside the beaker is water. If I go ahead and fill the beaker up with a rock, let's say, toss the rock in some, let's say I told, words, how do they work? You know, let's say I have my, okay, hold on here. Let's say I toss a rock into my water. What's going to happen to that water, and I'm going to go ahead and fill it. What's going to happen to my water is that it's going to raise a certain amount. I'm just going to draw that from the side here. So my water was originally at this level, and I'm just going to draw lines here. Water is originally at this level. I throw in a rock, get from this level. The difference, paint like that. Let's do this. The difference here, the amount it raises, is the volume of this rock. And so that's what it means to displace something. So in this question right here, I toss a piece of magnesium into some water. By the way, don't do that. Pure magnesium, I believe, will react violently with water. Although, I might be thinking of sodium instead. I probably am thinking of sodium. Anyway, magnesium into water. Water rises by 2.76 milliliters. We're just asked what the density is. If we remember, to calculate density, we need mass over volume. Zoomed in a little bit. I didn't need to do that. So mass is 4.8 grams. 4.8 grams. The volume is 2.76 milliliters. Just divide them, and we'll get our final answer. That there is. Go ahead and clear all these. Everything. That's what I always assumed. CE stands for 4.8 divided by 2.76. So our density is 1.74 grams per milliliters. It is very important that we always include our units from now on going forward. Very soon, they'll become extremely important, especially when we start talking about atoms going into molecules, right? Hydrogen atoms turning into water molecules. These units will become very important. You don't want to mess up the math here. Next up, we'll highlight the yellow, great. The density of a gas is 0.68 grams per milliliter. We're asked to find the amount of space 23.8 grams of gas would occupy. So amount of space, that's volume. To figure out the volume, we just divide mass by density. So 23.8 grams divided by 0.68 grams, and I'll just put these in grams per milliliter. That's going to equal something. Figure out what that something is by going to our calculator. So we have 23.8. Okay, hold on. I'll block on 23.8 divided by 0.68. That's 35 milliliters of space. Done and done. Okay, now this is a two-part question, and it's not exactly typical here. We have a room temperature object, and it's got a mass of 25 grams, and it displaces 15 milliliters of water. So we toss an object into water, it rises back 15 milliliters. That's its volume. What's the density? Well, we already know what density is. That is grams per milliliter. So 25 grams divided by 15 milliliters. Well, that's going to give us our volume. So we'll go ahead and clear everything. 25 divided by 15, 1.66 or 1.67 grams per milliliter. So that's our density. Done deal. Now we cool our object down. So it's at 20 degrees Celsius, and we cool it down to the point where it has half of its original thermal energy. Now that is important. Half of its original thermal energy. What would its temperature be in Kelvin and in Celsius? Really, Kelvin should be capitalized. That's not. So there's a reason I bolded and highlighted half of its original thermal energy. Now, you might think to yourself, okay, 20 degrees Celsius, half of that is 10. Don't get fooled here. Half of 20 degrees. This is a scale, the Celsius scale goes all the way down to negative, I think 210 or something, 270 or something. Let's go ahead and figure that out with our images here. This one is the one we want. And let's go ahead and zoom all the way in. Maybe not all the way in. So with this image, we see here that 20 degrees Celsius would be somewhere around here. Half of 20 degrees Celsius is not 10 degrees, because that would just only take you down like a few things like down to here. We don't want that. We want half of its energy. So half of that would be somewhere around here, negative like 100 something. So what we're going to do first is we're going to first convert 20 degrees Celsius. We're going to first convert 20 degrees Celsius into Kelvin, which is this scale up here. So 0 degrees Celsius is 273 Kelvin. Negative 273 is 0. So the scale is pretty set. To turn something into Kelvin, or to turn Celsius into Kelvin, all we had to do is add 273. There's a decimal that goes after it, but we're just not going to deal with that here. 20, I don't like that. I don't like how that works. 273 plus our degrees Celsius will equal our temperature in Kelvin. Notice there's no degree sign. So our temperature in Celsius is 20 degrees. So 273 plus 20 degrees is 293 Kelvin. Of course, this isn't any answer we want. We want the temperature in Kelvin after it's halved. But it's really easy to have this. Just divide it by 2. So, clear everything. 293 divided by 2. 146.5. Let's go back here. And start back drawing. 146.5. And so that's one of the answers we want. We want our temperature in Kelvin after the object loses half of its energy. And so that's one of them right there. Next, we're going to turn this back into Celsius. And to do that, we just rearrange this, right? How do we arrange it? Let's just subtract 273 on both sides. If we do that, C is left by itself. K is still in the same spot, and we just subtract 273 from both sides. There we go. So we take this number, and we subtract 273 from it, and we'll get our temperature in Celsius. Back to here, draw it in. Our temperature of our object after it loses half of its energy is not 10 degrees Celsius. It is actually negative 126.5 degrees Celsius. Great. So we're going to clear that off. We're going to exit that, and we're going to go over here. Let's see, how do I close that? There you go. Scroll back down to assignment number 3. And so we have our temperatures. Our temperatures were 146.5 Kelvin and negative 126.5 let's see, degrees Celsius. Then that's it. Now, this is where conversion factors get fun. What is the quantity represented by the following fractions? 3 over 3. What is 3 over 3 equal to? That is 1. 12 eggs and 1 dozen eggs. What does that equal to? Same amount of eggs. 1 meter, 100 centimeters. It's the same length. So what is this question getting to? This question is getting to the idea that conversion factors are talking about the same thing, right? If I have 100 pennies and $1, I'm talking about the same amount of money. If I have, let's say, 473 grams and 1 pound, I'm talking about the same weight. If I have 12 eggs and a dozen eggs, I have the same amount of eggs. And so conversion factors are talking about the same thing. If we take a look at these conversion factors, 1 gram and 1,000 milligrams, they're talking about the same amount of weight. 1 kilogram, 1,000 grams, same amount of weight, so on and so forth, right? So what a conversion factor is it's something that lets us, convert units, which is handy because oftentimes American units seem to make no sense, whereas metric system units are just multiples of 1,000 or 10 or 100, however you have it. So let's take a look here. We have Alex. Hi, Alex. He buys a drink cart. It's got a pint in it, a pint of whatever drink he has, and we're being asked how many milliliters of the drink is Alex going to consume if he drinks the whole thing. And so what we need out of here, there it is. What we need is a plan. We need a plan to turn pints into milliliters. Let's take a look at what conversion factors we're given. Let's try to find pints. Here we are. Pints turn into cups. Okay, sure. Pints turn into cups. What do cups turn into? Cups turn into quarts. Do quarts turn into milliliters? No, they don't. Do cups turn into liters? Yes, they do. And then liters turn into milliliters. So our plan is pretty straightforward. We're going to take those pints, convert them into units of cups, and convert those cups into liters, convert those liters into milliliters. That's the plan. Now, let's get started. The way I prefer it in my class will be to insert tables, right? We have 4 conversions to do, another for the math, and 1 more for our final answer. So we're gonna need 6 columns, 2 rows. We're gonna color the first one, leave this one. We're gonna color that in green because green to me means go. We're gonna color in the part where we do our math yellow because that means slow down. And we're gonna color in our last one as red because that's our final answer. And so when we're thinking about this, we have 1 pint. That's our starting material. But Alex here has 1 pint. How many cups does 1 pint turn into? We want the cup value on top because our plan calls for cups. 1 pint turns into 2 cups. So 1 pint goes on the bottom there. How many cups? The next thing we're going to turn into liters, so 1 liter. And 1 liter is equal to 4.23 cups. 4.23 cups. Lastly, we're going to turn liters into milliliters. So 1 liter is equal to 1,000 milliliters. Done. Next thing we're going to do is we're going to make sure our units cancel each other out. Now this part I have a lot of confusion with. I typically get a lot of confusion with. So let's go ahead and get rid of these beakers with water and rocks in them. Let's go ahead instead and talk about math for a second. Let's go ahead and get the brush. Let's say we have 3, right? Let's say we have 3 threes. Let's do bigger. We can do bigger. We have 3 threes, and they're all being multiplied. Right? If we do that, another way to write this, which is equivalent, is 3 to the power of 3. Okay, cool. We know that. It works with the units too. If we have, let's say, pints, feel free to be amazed at my drawing. If we have pints times pints times pints, that word's going to get real annoying. You would have, this is equal to pints cubed. Right? So if you're taking the volume of something, you would have pints cubed, and we don't want that. We want units to be gone. And so let's go back to the example with the threes. If we have 3 over 3, we already know this turns into 1, right? 1 over 1, which basically means nothing, right? We take 3 over 3. If we had, let's be all this. If we have 3 times 4 over 3, that's the same as saying 1 times 4 over 3. This is just like 6th grade algebra, right? Or 1 over 3, my bad, 1 over 1. So it's just 4. These things cancel each other out. These things cancel each other out. And so it's the same thing with our units. If we have pints and cups, if we have pints times cups over pints, we need to have them on opposite sides. Right? Just imagine that there's an imaginary 1 right here. Pints here will cancel each other out, and our final answer, our final unit will be in cup. So always make sure, if we're trying to get rid of units, if we're trying to convert them into other types, you got to make sure the conversion factors are on opposite sides. That way they cancel each other out. And so pints over pints, canceled. Cups over cups, they're canceled. Liter over liter, they're canceled. Only one that remains is milliliters. So we're going to take 1, 2, 1, 1,000. We're going to multiply it all together. 1 times 2 times 1 times 1,000, that is 2,000 milliliters. Because that's the only one that's left. 1 times 4.2 times 1, that is 4.23. Our final answer. I've got a lot of tabs open. Clear everything. The final answer is 2,000 divided by 4.23. That's equal to 472 milliliters. 472 milliliters. We're going to do the same thing for numbers 8 through 9. So what is the plan? Highlight this thing because we got to always have a plan. Going in, you just can't, go willy-nilly. Got to have a plan. We have 1,500 milliliters, and it shows its values in pints. How many pints of water should Marco measures out? Well, this is just the opposite. We have milliliters, and we want them to turn into pints. So we're going to just kind of work our way backwards here. Like that. Turning milliliters into liters. Turning liters into cups. And turning those cups into pints. That's our plan. Go ahead and insert a table. 4 for our conversions, 1 for our math, and the last one for our final answer, and 2 rows of the stuff. The first column will be green, because green means go in my head. Second to last one is our math. Slow down, make sure you're right, check your work, and the last one is red, our final answer. We start off with 1,500 milliliters, and we're going to go work our way backwards. We're turning milliliters into liters, so 1 liter goes on top. 1 liter is equal to 1,000 milliliters. Great. We're turning liters into cups, so 4.23 cups goes on top. 1 liter goes on the bottom. Cups into pints, so we know 1 pint is 2 cups, and we're good to go. Milliliters cancel out, liters cancel out, cups cancel out. Our final answer is in pints. So we clear all these out. 4.23 times 1,500. That's 6,345. 6,345 pints. Always keep track of your units. 1,000 times 1 times 2, that is 2,000. No unit, because at this point they've canceled each other out. So let's just do the division. Divide by 2,000. 3.17. All right, done. Last one. Now, for this one, there's something here you have to realize. The first number is not, the first number may not be, the first number you see may not be the first number you put in this box. So be aware of that. Ava buys a package of food. The nutrition label says that 1 serving is equal to 36 grams and has 110 calories. So here's a conversion factor for you. Make a note of it. You've got conversion factors, and let's go ahead and highlight these. Conversion factors. What are the conversion factors? You have 1 serving equal to 36 grams. That's a conversion factor. 36 grams is equal to 110 calories. Okay, so now we have a conversion factor. We have 1 serving is equal to 36 grams. 36 grams equals 110 calories. If we use that kind of, I think the property is the cumulative property. It's one of your base, properties. 1 serving is also equal to 110 calories. Let's keep going. The box is printed with a label that says 0.150 pounds. Ava eats the whole package. How many calories did she eat? Okay, so how much food did she eat? That's what we want to start with. The plan, therefore, is to start with how much food she ate. She ate the package. That's measured in pounds. We want to turn pounds into calories. Okay, how are we going to do that? Well, to get calories, we need grams. Okay, so let's go ahead and turn pounds into grams. Can we do that? Let's look at our conversion chart. Let's try to find anything with pounds in them. Oh, we have pounds right here, and it turns into kilograms, and kilograms turn to grams. So this is another 4-step kind of process. We're going to turn pounds into kilograms, turn kilograms into regular grams, and then those grams into calories. So now we have our plan. It's a 4-step plan, which means we need 6 columns. 4 for each of those steps, a 5th one for our math, and a 6th one for our final answer. The first box is going to have what we start with. The second to last box is going to have our math in it. And the final box will have our final answer. So what do we start with? We start with 0.15 pounds. That'll make it neat. We know that 1 kilogram is equal to 2.2 pounds. Always make sure you have your units on the opposite side, and also just keep track of your plan. Pounds to kilograms, that makes sense. We know that 1,000 grams is equal to 1 kilogram. And we know based on our answer here, or our scenario here, that 110 calories is equal to 36 grams. Capitalize these. The nutrition labels are measured in kilocals. So we have units cancel out, units cancel out, units cancel out. We're good. So let's do some math. We have 0.150 times 1,000 times 110, 16,500 that out, calories. A shorter way to do it. Next up, we're going to do 2.2 times 36, 79.2. No units, because these all have canceled each other out. Let's figure that out. 16,500 divided by 79.2, 208 calories. Now, she's eaten, if I wanted to go further, I can. She's eaten 208 calories. How many servings is that? Well, I know that 110 calories is 1 serving. And so if I wanted to go further, I could just divide this by 110. And I could see that she ate 2 servings of whatever package this is. I say 2, it's really 1.9, but really at that point, it's 2 servings. Come on, Ava, calm down. So this is how we're going to do this type of math, right? Always have a plan in mind, have your second box for just the math, and then your final answer. Now, this assignment is important enough for me to not just delete this out of hand like I do with assignments 1 and 2. I'm going to leave this math up here because it is that important for us to get the hang of these conversion factors. So I'm going to leave this up, and you guys will see me in an assignment number 4 video when that comes up next week. Until then, we have our notes that we should have practice with, but go ahead and just, I believe, check out this this video by, I think her name is Melissa. Great resource right there. And I'll see you all in another video. Bye-bye.